A PID controller is very rarely operating alone in a single loop feedback control scheme. Very often, by making additional process measurements, we can augment the complexity beyond simple single loop control. The idea, of course, is not to increase the complexity, but to improve control performance. This leads to more complicated control structures involving nested control loops. The control scheme will combine feed-forward, cascade control, decoupling, and so forth. In this section, we will present all the necessary ingredients to construct a good control structure, but more importantly, and this is probably the main message of the course, we present a systematic procedure to obtain a good control structure. We will illustrate this using a very simple example. The methodology to construct the control structure is obtained by considering 5 items, as you can see on the screen, and this will work for very simple processes but also for more complicated processes. The first thing that you have to do is to look at the control objective, and by looking at the control objective, what you will fix a list of possible PVs, right? And we will see later on in the course how you can select the appropriate PV. Once PV is fixed, well, you can look at the possible manipulated values, well, manipulated values that can influence the PV that you've chosen, and most probably you'll come up with a list of possible MVs. The third item is to look for disturbances in a very systematic way. As you know, there are 2 types of disturbances: output disturbances and input or load disturbances. Output disturbances, if a measurement of the disturbance is available, can be rejected using feed-forward. Load disturbances can be rejected using a local feedback if a local process variable is used to detect the load disturbance. This leads to cascade control. We will see that listing potential load disturbances and the use of cascade control can help us reduce the list of MVs that we had obtained after the second item. The fourth item is to look for a list of potential constraints in the process. For example, saturation limits of an actuator, or minimum and maximum values for certain process variables and their derivatives. We will see later in the course how we can take these constraints into account in the control structure. Once the control structure has been designed, you will have to tune the different components, and therefore you'll need process behavior knowledge, right? So for instance, to tune the controller, most probably a PID controller, you'll need information about the relation from manipulated value to process variable. This is really the input-output process dynamics. To tune the feed-forward action, you'll need information on the relation between the disturbance variable and the process variable, and this is really the disturbance dynamics. You'll also have to implement the constraints in the structure, right, in the control structure, so you'll need information about the relation between the manipulated variable and the constraint variables. If you're interested in control structures, this is a very nice paper on the systematic analysis of control structures. Most practical problems are not, as you might think, related to just PID optimization. Most practical problems are related to process problems, so process Problems are, for instance, sensor problems, actuator problems, and problems related to the control structure. So before you start thinking about optimizing the PIDs, it is important that you solve the process related problems and the problems related to the control structure first, as it is impossible to compensate for the wrong controller structure or to compensate for a process problem by optimizing a PID controller. And this is why we talk about controller structures before we talk about PID controllers and PID tuning. If in the future you're responsible for a production line, you should monitor all control loops on a regular basis. This used to be very time consuming, but nowadays control performance monitoring tools can assist you and greatly simplify your job. Here on the screen you see an overview of the plant performance using the Control Performance Analytics tool CPA from Siemens. Other vendors will offer similar tools. Production data is used to compute key performance indicators for tracking and disturbance rejection behavior. It is also possible to detect oscillations, stiction, and controllers in manual mode. As you can see, the control loops are ranked according to priority of action. The control loops that are above are the ones that require most attention. Well, there is a recommended action, and among the recommended action you can see that, well, the system is drawing your attention to, for instance, oscillation, so this is detected automatically, or stiction performance. You can see that in some cases the recommended action is optimization of the control loop, and the system will actually provide a new set of control parameters. Well, once you have detected the problematic loops, what you can do is, of course, deal with these loops, and you should check and correct, well, first the instrumentation and actuator problems. Problems related to instrumentation are, for instance, problems that have to do with calibration of sensors, and we have seen that actuator problems are very often valve stiction problems. Then you can look at the control structure and adapt the control structure by using, for instance, feedforward cascade control. Very often what is happening is that a cascade control is implemented, but that it is not well implemented, in the sense that the interlocks are not correctly implemented. We'll deal with this problem later on in the course. Once you have checked and corrected these problems, you can think about PID tuning. Do this tuning and check performance again. If you're not happy with the performance, it could be that the control loop that you're examining is a candidate for more advanced process control. So for instance, it could be that you have a process with a lot of dead time, a dead time that is much higher than the main time constant, or that you have a, between quotes, slow process, several time constants in series. And if you have this large dead time, you can use a Smith predictor. And if you have this between quote slow process, well, then you can use a predictive PID controller. In the case of complex dynamics, okay, again, if you have a large dead time with respect to the main time constant, or if you have, for instance, an inverse type response, you can use internal model control. If the process has strong nonlinearities, in the sense that the behavior is very different around very different working points, then you can use gain scheduling or controller scheduling. And if the process is multivariable, you can use decoupling. All the methodologies that I've just talked about are dealt with in this course. For multivariable systems, you can also go for model predictive control. This methodology is not tackled in this course, but the students in control engineering have learned about this strategy in the course Model Predictive Control by my colleague Thomas Muser. We will now go over the first 4 items of this methodology, the systematic methodology to construct a control structure. Item 5 has been considered in the previous section as it deals with process behavior, right? So we'll start with the choice of the process variable. Let us start with item 1 in our procedure to construct a control structure, and this item 1 deals with the process value. Well, what is very important is to look at the control objective, and this control objective will dictate the process value. Well, very often there will be several candidates that you use for your control, right? And you have to select one of these candidates. So the selection criteria are, well, first, accuracy and repeatability of the measurement. And you have to beware, of course, of measurement noise. So this is a slide that I've drawn from the course of system identification, and what we do here is test the repeatability of a measurement. We assume that the correct value is here at the center, right? So what we want is a measurement with a low bias and a low variance. The bias is the difference between the average measurement and the correct value. So you can see here that the average measurement is over here, and this is far away from the correct measurement, so we have a high bias. We want, of course, a low bias, but we want also a low variance. The variance is the variability around the average measurement. You can see here that, well, the average measurement produces a correct measurement, but since there is so much variability, we do not like this sensor because the variance is too high. So the ideal sensor has low variance, low bias. Note that you can correct the bias by calibrating the measurement. It's much more difficult to do something about the variance. Of course, we also have to look if there is a sensor available to obtain a measurement of PV. We have to look if this sensor is reliable and that it comes with a reasonable cost. And then finally we have to look at the timing, right? There are 2 aspects. The first one is the sampling period, and the second one is the delay that is introduced. We have to look at the documentation, and we can find the minimum sampling period and see if it is good enough for our control purposes. The delay, well, that's the delay coming from the sensor itself and then from its location. If none of the candidate PV meet the 3 conditions on accuracy, availability and timing, we'll have to look for a substitute information source. So for instance, a soft sensor. A soft sensor is a mathematical model that will allow you to estimate PV on the basis of other measurements available on the process. Students in control engineering will remember that a soft sensor might, for instance, be an observer-based estimate. Let us talk now about the sampling of the process value. The sampling interval should be as big as possible, but as small as needed. This is kind of a catch-all phrase to tell you that there is a kind of trade-off here. An advantage of a small sampling interval is that your control algorithm will run more often, and therefore you'll have to wait a shorter time until the next correction. And you'll see also smaller changes in the manipulated value. Of course, the advantage of a large sampling interval is that you use less computer resources. So you can see here indeed that there is this trade-off. Remember that the numerical resolution, this is the quantization step, is restricted. So it makes no sense to sample above a given frequency, because the actual difference between two successive measurements will be so small that you will not see it on the numerical quantized signal. An indicative value for the sampling interval TS, in the case of set point tracking, this is important, is that you should have 10 samples per rise time. Okay, so for instance, if you have the open loop step response, right, this means that, for instance, you put your controller in manual mode and you do a change of MV, and then you look at the evolution of PV, which might look like this, for instance, right? Then you remember that the rise time is the time that the process value takes to go from 10% of the steady state value to 90% of the steady state value. So this time over here is the rise time. So in this period you should have 10 to 15 samples, right? So this means that, well, the sampling frequency is of course system dependent. Very often the sampling frequency will be chosen much higher than what is advocated by this rule. This is because we want to use PV for process troubleshooting. So we want to detect spikes, and we want to see if the process variable PV is reasonable, right? We want to check the plausibility of the signal, and for that we can look at the slope at the gradient. For instance, if we have a grammage of 100 grams per square meter now, it is impossible that 1 second later suddenly the grammage is 120 grams per square meter. So what is done is that a block is programmed, and it's called a gradient check, right? At the input, of course, you have PV, and here at the input you have parameters with limits on the slope, right? So what this block does is monitor PV over a certain period and compute the slope. If the slope goes above a certain limit, then a flag is set, and the PV here that comes out is frozen. So this is PV out here, it is frozen, right? And this flag can then be used to lock the controller and to send an alarm, right? And then what the user can do, well, is kind of see what has happened, and if everything is all right, again give a reset to this gradient block so that PV out is again the PV at the input. Note that for a disturbance rejection problem, the sampling period is also dependent on the nature of the disturbance, and this might also lead to a sampling frequency that is much higher than given by this rule. When sampling PV, the process value, we have to make sure, of course, that we prevent aliasing, and there are two ways to do this. Well, the first way is to sample faster than the fastest frequency component that is present in the input signal, but this, well, fastest frequency is not always known. So what is done instead is, well, that you install an analog aliasing filter that will remove all components above the Nyquist frequency before the sampling is actually done, to prevent aliasing from occurring. If we fix TS and we use this analog anti-aliasing filter, well, remember that from the Nyquist theorem we have to remove everything that is above the Nyquist frequency, and this is pi over TS, right? What we'll often do is use an anti-aliasing filter that is simply a first order low pass filter, right? And this filter then comes with a time constant, right? That is the time constant of the anti-aliasing filter, and we'll write it like this. Okay, but since we're using a first order low pass filter, if we take 1 over this time constant to coincide with the Nyquist frequency, we'll have kind of a very poor attenuation at the Nyquist frequency and just after the Nyquist frequency. So what we have to do is to choose 1 over this time constant sufficiently to the left of the Nyquist frequency. So if you take the time constant of the anti-aliasing filter to be 1.3 times TS, we'll have a cutoff frequency of the first order filter that is 1 over 1.3 times TS, right? And given the frequency behavior of a first order system, what we'll have here is an attenuation, right? And if you use a time constant of 1.3 TS, you'll have an attenuation of 12 dB at the Nyquist frequency. If you take a time constant that is slightly higher, then you will be even more to the left, right? So you'll have 1 over 3 TS as cutoff frequency, right? And we'll now have this behavior over here. This is just indicative, of course, and you can see that at the Nyquist frequency you'll have even more attenuation, and if you look at it, well, it will be minus 90 dB at the Nyquist frequency. Here we have used a first order filter, but if you use a higher order filter, and typically you can use Butterworth type filters, look at Matlab and type help butter, and you will see that you can construct low pass filters of higher order. Okay, since they have higher order, they will have a higher slope here after the cutoff frequency, and you'll be able to approach the theoretical minimum, which is a high order filter with a time constant that is TS over pi, and this is really 1 over the Nyquist frequency. Well, let us investigate this in Matlab. So what we'll do is take TS is equal to 1, right? So the Nyquist frequency is 2 pi over TS divided by 2. What we'll do is use a first order filter, and we'll use the time constant for the anti-aliasing filter to be 3 times TS, and we'll have a look at the Bode diagram. We'll then take a second order filter, and we'll use a second order filter with 2 times the same time constant, right? And the time constant will be 1 times TS, And again, we'll look at the frequency behavior, and then we'll take a Butterworth filter, right? And it's a Butterworth filter of order 5, right? And we will again look at the frequency response of this Butterworth anti-aliasing filter. Well, let us now run the code and let us look at the first figure. This is the Nyquist frequency over here, right? Which is, because Ts is equal to 1, we have a Nyquist frequency at, well, pi, right? Here we have used this first order filter with time constant 3 times Ts, so the cutoff frequency is at 1/3, since Ts is equal to 1 here, so the cutoff frequency is approximately over here. And we can see indeed that we have to put the cutoff frequency to the left, sufficiently far from the Nyquist frequency, so that we have sufficient attenuation at the Nyquist frequency. So here the cutoff frequency is at approximately 0.11 of the Nyquist frequency, right? So we can see that if you use the time constant is 3 times Ts, we have indeed an attenuation of -19 dB. Let us now have a look at the second order anti-aliasing filter. We have now 2 time constants, right? And the time constant is 1 times Ts. We can see that the cutoff frequency has moved to the right, since it is now 0.32 times the Nyquist frequency. And we have been able to do this because, of course, the slope in the high frequencies is now of -40 dB per decade. And notice that we still have an attenuation of approximately -19 dB. Well, let us now look at this fifth order Butterworth anti-aliasing filter, and again the cutoff frequency, so that's the frequency at -3 dB here, has moved to the right. We are now at 0.65 times the Nyquist frequency, and as you can see, we still have an attenuation of around -19 dBs, right? We can do this because now the slope at the high frequencies is of -100 dB per decade. Well, the reason why we like a high order Butterworth filter is that we provide sufficient attenuation at the Nyquist frequency, and we do not provide attenuation over a too large frequency range just below the Nyquist frequency. Indeed, with a first order anti-aliasing filter, we provide this same -20 dB at the Nyquist frequency, but we're also attenuating in a large frequency range below the Nyquist frequency. We would like to implement, of course, the perfect anti-aliasing filter, but it is impossible to implement such an analog anti-aliasing filter in practice. We will see later that we'll also sometimes have to implement a digital anti-aliasing filter. This is when we change the sampling frequency, and even in this case the order is restricted because this would lead to numerical problems if the order of the Butterworth filter is chosen too high. Once a signal is aliased, this means that it presents itself at a frequency that is lower, much lower than its actual frequency. Well, there is no way to retrieve the true actual signal. It is important to realize that aliasing can still occur between the analog to digital conversion and the controller, so this means later in the control chain. This is true even if aliasing was prevented during the first digitalization step. It is really the final sampling rate that governs aliasing. So anti-aliasing filters are required before each sampling or resampling operation, right? If it is sampling, then you need to use an analog anti-aliasing filter, and if it is resampling, then you need to use a digital anti-aliasing filter. Let us illustrate this because this is important. Assume that we have a PV and that this is a digital PV. It has gone through the analog to digital conversion, and we have sampled the signal with a sampling period TS. We've been choosing TS rather small because we want to compute or to do gradient check monitoring, right? Remember that we can do this to kind of troubleshoot the system and detect if there is something wrong with this signal over here. And here we'll have a PV out. If there are no problems, well, PV out is equal to PV. If there is a problem, well, this value will be frozen until the operator intervenes, right? Well, suppose that this PV is used for control. Typically what, and this will be, for instance, a PID control. Typically what you should do, let us assume that we're doing tracking over here, so we have a tracking problem. Well, you should look at the rise time, right? So you can kind of look at the step response, right? We look at 90% of the steady state response and 10% of this steady state response. This will be somewhere over here, this will be somewhere over here. So this is the rise time, and since we have taken TS so small, we kind of see here, oh, we have too many samples in a rise time. Okay, so I will use for control another period which I will call TS control. So this means that this algorithm will run every TS control, and typically in this case we'll use TS control much larger than the TS that has been chosen over here. Well, this controller will use a set point and a PV, and what you cannot do is connect the two because you have a resampling operation. You go from a TS to a TS control that is much larger than TS. So you need here a filter which is a frequency anti-aliasing filter, right? And this filter will have to remove everything that is above the new Nyquist frequency for control, and this one is equal to, well, pi over TS control, right? So whenever you have a resampling operation, this means that you change the sampling frequency and you increase the sampling period, you have to introduce a frequency anti-aliasing filter, and in this case here this will be a digital frequency anti-aliasing filter. Typically this digital low pass filter will remove the high frequency noise that is present on PV, and it will make sure that this high frequency noise will not alias to low frequencies because of the resampling operation. The process value is often subjected to noise. The origin of the noise can come from the process. An example of that is dithering valves. This dither signal is added on top of the control signal to prevent friction, right? But it is also causing, well, variation on PV, noise on PV. Another example is surface ripple in level measurements. You have that in tanks when the input flow enters the tank from above, causing this surface ripple. Well, most often the noise is coming from the measurement itself, so from the sensor itself. It could come from the sampling system. Remember that the resolution is finite, so there is quantization noise. It could also come from the signal transmission, right? And it could also be associated to this variance on the measurement that we talked about previously. The noise is very often random in nature, but it could also be periodic and lead to spikes. If random in nature, we can characterize it by its distribution, so for instance a uniform or Gaussian distribution, and we can also characterize the noise by its frequency range, and most often the frequency content is in the high frequency ranges. In the time domain, the noise can be characterized by the signal to noise ratio, and what you can do is compute the mean and the variance using these formula. If you need the variance, use this formula over here. Remember that you might need the variance or the standard deviation to do set point optimization, right? You will need a running variance, a moving variance, and for this you can use this formula. You'll have to keep track of the sum of the measurements and the sum of squares over a certain period, but once you have kept track of these sums, you can compute the variance and therefore also the standard deviation very easily. If you use this formula, you'll have to compute the mean first and then compute the variance using this formula, but this will require 2 for loops. So this is the easiest formula to implement a moving variance or a moving standard deviation computation. You can of course characterize the noise in the frequency domain, and therefore you can use your best friend from the course of signals and systems, the fast Fourier transform, or FFT. You will see that in practice the noise dynamics are very different than the process dynamics, and typically the noise content will lie more than a decade above the bandwidth of the system. For filtering, usually a first order filter or a lag filter is used. You can also use a moving average filter. This filter will actually average the values over the last X samples, and you can also use more complex filters such as Butterworth filters, but they are not always available in the libraries associated to the PLC. Well, in practice, of course, you should use the filter to remove the noise, but the signal should be left intact, right? So what we do is use the filter for noise reduction, and in general this should not be a problem because we have seen that the noise and process dynamics are generally very different. If there is signal distortion, then you need to correct the filter time constant. Well, of course, the filtering procedure is influencing the process because the controller is seeing the filtered PV, right? So if you use first order filtering, well, the order of the process is increased by 1, and this filtering, this first order filter, as we have seen, will introduce phase and amplitude distortions, right? So it might be necessary to redo the controller tuning. So the procedure is that you first have to filter the PV, choose the appropriate time constant, and when you're ready, you can start the tuning exercise of the PID controller. Beware of the initialization of the filter in a control loop on a running machine, because you're going to take a block from a library, compile and download. You have to make sure that this filter has been properly programmed so that the initialization is done in a good fashion, and so that's when you run the code the first time, well, the filtered PV is initialized properly. If it is initialized, for instance, to 0, this will be very problematic for the control loop, as it would take roughly 5 times the time constant for the filtered PV to reach the actual PV. The proper initialization procedure has been illustrated when programming an FB that implements a first order system in the previous section. Before we continue, a short parenthesis on the control system layout. The control system is made up of 3 units. Input processing, this is the processing of PV or the processing of the control error. Control processing, this is the implementation of the actual control algorithm. And then finally output processing, this is processing of MV, the manipulated value. Sometimes the 3 units are programmed using the same FB, that is the same function block. There are reasons why you would like to separate these units over several FBs. For instance, this would allow you to run the input processing and the control processing at different speeds, and we will illustrate this using an example. As said before, input processing is the processing of the input of the controller, that is PV, and the control error SP minus PV. The processing includes filtering, checking of the validity of the measurement using a gradient check that we have, for instance, presented before, and normalization, that is to go from a PV in units to a PV that is normalized as a percentage of the measurement range. The control processing unit processes the set point and the process variable PV to propose a control action MV, and it is the control algorithm, of course, that determines the name of the controller. If it is a PID control algorithm, the controller will be a PID controller. If it is, for instance, a model-based algorithm, we'll deal with a model-based controller. The output processing unit checks the feasibility of the control action. It will implement actuator saturation and rate limitation of MV, making sure that there is no wind-up of the control action. It will also implement the interlocks and the different control modes that we have introduced in section 1. And finally, the control action is denormalized to go from an MV, the control action in percentage of the actuator range, to an absolute MV. Note that it is more difficult to separate control and output processing, and very often the 2 units will run at the same speed. As mentioned before, the input, control and output processing are sometimes performed in different function blocks. Modern PLCs will have different cycle times. Some cycle times are fixed and others are varying. The fixed time cycles go from several milliseconds to several seconds. As indicated, the associated time cycles, or also called sampling periods or processing periods, have a fixed duration. Blocks that are running using this fixed time cycles will run at a regular pace. This is of course required to run the difference equations that will, for instance, implement a first order or PID relation. As you can imagine from the name, blocks implemented in a varying time cycle will run at an irregular pace and are not suited to implement recurrent type equations, but you can use them to implement, for instance, a static relation. In theory, it is also possible to implement a dynamical system using a varying time cycle. This means that you have to keep track of the time that has passed since the last time the block was processed, and this makes things a little bit more difficult. Well, you can now use different fixed cycle times to run, for instance, the input processing faster than the control processing, and this will allow you to do process troubleshooting or to filter PV while not wasting computing resources for control processing. This will be illustrated shortly. Let us look at the use of different cycle times for a filtering plus control application. PV is a digital signal and it has been acquired without aliasing with a sampling period, a sampling interval of TS. An open loop step response has been performed, and as you can see, the resulting response is noisy. The first thing that we can do is determine the open loop time constant, and for this we use the tangent at the origin method, right? Next, PV is, well, influenced by noise, so what we do is use this first order filter to remove the noise. This filter will be running with a cycle time that is also TS, so the cycle time of the first order filter, the TS of the filter, is the TS that has been used to acquire PV, right? And the time constant is of course smaller than the open loop time constant of the process. The idea is that you remove the noise but that you leave the base signal intact. And if you do a good job, this is how the filtered PV should look like. What we could do is run the control algorithm at the same pace than the first order filter, but usually PV is acquired with a TS that is much smaller than needed for control. So using the same cycle time would lead to a waste of computational resources. In practice, you should use a cycle time for control that corresponds to the rise time of the system divided by 10 or 15. In this case, we have chosen the cycle time for control to be the open loop time constant divided by 10, which is approximately the same idea as using the rise time divided by 10 or 15. In general, the controller will run at a cycle time TS control that is much higher than the cycle time of this first order filter, TS filter. There is a resampling operation in between the filtering and the controller, right? So we have to make sure that we do not have any aliasing, and therefore this filter will also be playing a role as an anti-aliasing filter, and we have to make sure that the time constant of the filter is larger or equal to 1.3 times the TS for control. This lower limit here of 1.3 times the TS for control will give an attenuation of 12 dBs at the new Nyquist frequency, which is pi over TS control. In the PCS7 system, the different fixed cycle times can be set in the hardware configuration of the CPU, and as you can see, in this case there are 9 different fixed time cycles ranging from 10 milliseconds to 5 seconds, and as you can see, the fastest time cycles have the highest priority. We have seen in the slides that you could run filtering and control operation at different cycle times. Another application of different cycle times lies in cascade control. I will not go into the details because cascade control is dealt with later on in the course. It suffices to say now that the internal loop that you see over here, or the slave loop, has a much faster dynamics than the external or master loop. So it makes sense to have this controller running with a TS that is much smaller than that of the master controller. What you see over here is the CFC plan that implements the Cascade control. You can recognize here the master PID controller and here the slave PID controller. So let us have a look in details. This is this master PID controller. It is running in a cycle OB32. OB stands for organization block, and in the hardware configuration we had defined the cycle time of OB32 at 1 second. So this master PID controller runs every second. If we now go and look at the slave PID controller, you will see that this PID controller of the slave PID is running with a cycle time of 100 milliseconds. So the associated TS is 10 times smaller. So as you can see, you can really associate a certain FB implementing, for instance, a PID controller to different fixed cycle times. What you see over here is the online variation of the varying time cycle using our emulated PLC, using PLC Sim, and you can see that the blocks using this varying time cycle run at an irregular pace. We can see over here that the shortest cycle time has been 10 milliseconds, the longest 120 milliseconds. That was probably at startup, and we set the highest cycle time at 6,000 milliseconds or 6 seconds, and this is the current or last cycle time. And if I push update, you will see that once in a while there is a variation in this cycle time, right? And this is because cyclic tasks have the priority. If executing the cyclic program takes more time, there will be a variation in the varying time cycle. In this case, the variations in the varying time cycle are small because, of course, we have emulated the process. On an actual process, some process events will cause temporary increases in the execution time of the cyclic tasks, resulting in an increase of the varying time cycle. Well, of course, in a fixed time cycle, let us say of 10 millisecond, right? All of the processing time must be done in less than 10 milliseconds, so that after these 10 milliseconds the outputs are available and can be set. On average, let us say that the processing time will be maybe 2 milliseconds. But because of events in the process, this processing time might vary, and in some cases, the calculations might be ready after only 4 milliseconds. This remaining time here, on average 8 milliseconds, but in this case only 6 milliseconds, is allocated to cyclic and acyclic tasks, right? And the cyclic tasks have the priority. So if there are variations here in the processing time in these fixed cycles, time cycles, right? This means that the varying time cycle will increase in this case because the processing time has increased. Okay, so changes in the processing time of fixed cycle times will result in variations of the varying time cycle, and this is what you see. As mentioned before, problems in control loops are often linked to actuator problems, sensor problems, and control structure problems. And therefore, before looking at the optimization of the PID controller, you should solve these problems first. This means also that you'll have to check if the measurement is accurate and reliable. The sensor performance can be degraded for a number of reasons. The main reasons are lack of calibration, use of the sensor outside its validity range, unshielded and faulty wiring, and external variables, very often temperature, that affect the sensor output. Let us now have a look at the process that we will consider as a tutorial example for the illustration of our systematic construction of the control structure. This example has been drawn from the book from T.E. Marlin, Process Control, Designing Processes and Control Systems for Dynamic Performance. What is nice is that the copyright of this book has returned to the author and that he is donating the book for use without charge. You can click on this internet link and this will lead you to a site where you can consult the PDF version of the book. This is what you get. This is the outline of the book, and you can, for instance, click on feedforward control. You can find the example that is treated in the course with its control structure, but you will find many other examples with associated control structure in this book as well. The process that we use as a tutorial example is a preheating furnace. It is, for instance, used to preheat crude oil in oil refineries. The preheating furnace is then located just in front of the distillation column. The product that needs to be preheated flows through the tubes of the preheater, receiving an prescribed amount of heat or energy. Oil, but also gaseous fuels, are used to generate the heat inside the furnace, also called heater. Here we'll assume that oil is used as a fuel. The control valve that you see over here can be used to adjust the fuel flow. Well, the objective here is to make sure that the temperature of the product flow at the exit of the preheating furnace is at a given set point, right? So over here, because of this control objective, the main PV that we'll use for control is the output temperature. In this simple example, the choice of PV, the first item in our systematic procedure to construct the control structure, is very easy. There is only one candidate PV here, the output temperature shown in red. In more complex systems, the choice might prove to be more difficult. We also have access to a number of candidate measurements to construct our control structure, but you will see later that we will not use all measurements. The candidate measurements are the input temperature of the product flow, the fuel flow, and the pressure inside the fuel line. In reality, you will see that processes that might look very different at first glance will be controlled using a very similar control structure. Here in this heat exchanger, the product output temperature is controlled by controlling the flow of heating medium through the heat exchanger. You can see that there is an analogy here with the preheating furnace, and you will see that the same ideas are applicable, leading to the same control structure. Well, in our systematic method to design the control structure, we have considered item 1. This is the choice of PV, and now we are going to consider the second item, which is the choice of the manipulated value. Well, we should use the following selection criteria for the manipulated values MV. The manipulated values should be responsive in the sense that they have a high influence on the controlled value or on the process value. So the gain from MV to PV should be sufficiently high. We also have to look at the timing. So this means that the time constants and the dead times that are involved in the relation from MV to PV should be as small as possible. Linearity is nice because it will simplify things, but it is not crucial. And the MV should have an influence that is as small as possible on adjacent loops. So the influence of MV on PV should be large, but it should be small on other PVs coming from other loops. If this is not the case, we'll have to introduce decoupling, and this will be tackled later on in the course. A very important remark is that the control structure should be as simple as possible, but no simpler. Right? This means that if you have to implement a cascaded solution, then you implement it, but in some cases it's not necessary. And if it's not necessary, well, then stick to a single loop solution because they are simpler, they are easier to tune, and they are easier to maintain. We'll come back to this later when we'll talk about the interlocks that you have to implement in cascaded solutions. We can now apply this on our preheating furnace example, and what we'll do now is list all the candidate MVs. So we're looking for potential influences on the output temperature. The first candidate that we consider is the product flow. Of course, this would presuppose that we have some actuator over here to influence the product flow. But of course you can see that if you restrict the opening over here, there will be less product flow with the same amount of heating energy, so the temperature would go up. So you can use the product flow here through the furnace to control the output temperature. But even if at the start this looks like a good idea, you can kind of feel that you cannot use it as a control of the output temperature because the throughput through the preheating furnace is of course determined by what is happening further down this process. It's not something that you can control, it's something that you have to live with. Okay, so this is clearly not a good idea. Well, let us look at the second candidate MV, and it's probably the most obvious candidate MV. Well, we can use simply the control valve to have our influence on the output temperature. Okay, this is going to be responsive, quick, but this will also have a non-linear behavior because most valves have a non-linear relation between input and output opening, right? So this, if you use this candidate MV, this will lead to a single loop control of the output temperature. Well, the third candidate MV is to use the fuel flow set point, and this means that you have to implement a local flow controller. Okay, and if you implement this local flow controller, you can set the fuel set point directly, right? And if you look at the overall solution for the temperature controller, this of course leads to a cascaded solution, right? You have a temperature controller that sets the fuel set point for this slave fuel flow controller, right? And this leads to a responsive, quick and linear behavior, because this internal loop here will have a linearizing effect. Well, the fourth candidate is to use the fuel pressure set point, right? And this means here that you have to implement a local pressure controller. And if you do this, well, you can set the fuel pressure set point directly and influence the output temperature, right? So if you look at the overall control structure to control the output temperature, again you have a cascaded solution. The primary controller is a temperature controller, and the internal loop or the slave loop is a pressure loop, right? When you compare this cascaded solution with the previous cascaded solution, you will see that it is not as responsive as the previous cascaded solution, because if you implement here a pressure controller, it will indirectly influence the fuel flow, so you might as well implement directly a fuel flow controller. Okay, so this one we will not consider, because the other alternative to use the fuel flow set point is more responsive. As a conclusion, we have retained two candidate MVs. So the first one is the most obvious choice, so it's the control valve, and the second candidate MV is the fuel flow set point, and this will involve here a local controller so that you can set the fuel flow set point, right? Both candidates are responsive, quick. There is a slight advantage with the fuel flow set point, because it will kind of linearize the relation from input to output temperature. To kind of decide which MV we will take, we'll have to look at all the disturbances that are acting on the preheating furnace and look at control structures that will allow us to reject them. So far in our search for a control structure, we have looked at item 1 of our systematic methodology. What is the control objective and what are the PVs, right? Previously we have looked at the candidate MVs and we have selected 2 of them, and now we are going to look at the disturbances, right? Where they are acting and how they can be rejected using given controller structures, and this will help us decide here on these candidate MVs. Well, for the disturbances, there are several questions that we can ask, but the 2 most important ones are these disturbances measured, right, directly or indirectly, but most importantly, where do the disturbances interfere with the process? If it is on the manipulated value, on the input of the system, then you know that this is a load disturbance, right? And then feedback can be used to reject the disturbance, and this will lead to a cascaded control solution. If the disturbances are acting on the output of the process, we speak of an output disturbance dV, then feedforward can be used to reject the disturbance. It is of course very important that both cascade control and feedforward still presuppose that all the necessary signals are available for measurement to implement the cascade control structure and to implement feedforward, right? For feedforward, we need to measure directly the disturbance, and for cascaded control we need a variable that will allow us to see that there is a load disturbance. Let us systematically list all the disturbances that are acting on the preheating furnace. The output disturbances that come into mind and that affect the output temperature are the product flow and the product input temperature. Assuming here that the heat energy that is produced is staying more or less constant, you can see that of course a product flow variation will affect the output temperature, and similarly if the input temperature is varying, well, you know that you'll have to put more or less energy to have the same output temperature. So if the heat produced inside the heater is constant, then a variation of the input temperature will have a direct effect on the output temperature. There is also a load disturbance that is acting at the input of the process on the manipulated value. Well, it's the fuel pressure. If there are fuel pressure variations, they will indirectly cause fuel flow variations, and these fuel flow variations will cause variations in the heating energy that is produced inside the furnace, and this will of course variations in the output temperature. There are other disturbances, but their influence is difficult to measure. For instance, the fuel heating value. If the fuel heating value is changing or varying, then the heat energy that is being produced inside the furnace will vary as well. Changes in the ambient conditions could also lead to more or less heating losses in the preheating furnace and thereby influence the output temperature. The heat transfer could be affected by coking on the tubes inside the preheating furnace, so that more or less heating energy is transferred to the product, affecting the output temperature. And finally, the product specific heat could be changing, right? The product specific heat is the amount of joules that you have to use to increase the temperature of 1 kilo of the product by 1 degree Celsius. If this product specific heat is changing, this will also affect the output temperature. The main difference between these 4 last disturbances and the other disturbances is that these disturbances are very slow with respect to the main time constants of the process, so that they can easily be rejected using feedback. Well, now that we have considered all the disturbances acting on the process, we can decide on which candidate MV we're going to take, right? Since we have here fuel pressure load disturbances, there is now really a big advantage in using the cascaded solution temperature, output temperature, fuel flow control, right? Because this local fuel flow control is going to reject the fuel pressure load disturbances much faster. Indeed, a fuel pressure load disturbance will cause a fuel flow disturbance, and this local controller will reject it immediately. The alternative, well, which is output temperature control directly on the valve, would be much too slow. Imagine now that you have this single loop controller controlling the output temperature directly on the control valve, when there is a fuel pressure load disturbance, the first time that you will see its effect is on the output temperature itself, and therefore you will react much too late. So in this case we'll have a cascaded temperature control solution. We'll have an inner loop and an outer loop. This is sometimes called the slave loop and the master loop. Okay, so this is the set point of the outer controller, and in our case this will be the temperature, right? And this is the PV of the outer loop, and of course this is producing the MV of the outer loop, but this will be the set point for the inner controller, right? And in our case this MV out here is the fuel flow set point, so it's in liters per minute, right? This has to be compared using the PV from the inner loop, and this is going to produce the MV from the inner controller, and here this is the valve position, right? This valve position, well, is going to influence the actuator opening, and therefore it's going to influence here the actual fuel flow, which is in liters per minute again. Of course you need a sensor, and this will then lead to a measurement of the actual fuel flow, right? This fuel flow will actually influence the actual output temperature, right? And again here you need a sensor to kind of measure this temperature, right? So here we had a load disturbance. Maybe I should put it somewhere over here, because it's acting on the input, and in our case it's the pressure in the fuel flow line, right? And there are two disturbances acting on the output. So this is the input temperature of the flow, right? And the input temperature of the product flow, and the product flow itself. Well, in order to be able to implement this cascade control for the output temperature, we need to have access here to the actual fuel flow. So this requires a sensor to measure the actual fuel flow. Notice that this cascaded solution is more complicated. Of course, we need to tune two controllers, the inner controller and the outer controller, and we'll see later on in the course when we'll consider cascade control. Well, we also have to implement this interlock strategy. Remember that we have discussed what would happen, for instance, if you put this controller in manual mode and you do nothing about the outer controller. Well, you would have integral wind up. Okay, so you need to implement the interlock strategy in a correct way, and we'll talk about that later on. But certainly if there are load disturbances present in the process, in our case fuel flow pressure load disturbances, it's really worthwhile implementing this cascade solution. The fuel pressure load disturbances can come from adjacent preheating furnaces. So if this is furnace 1, for instance, and well, that you have here the main fuel line, and that connected to this fuel line is another furnace 2, well, at startup or stop of this furnace there is a sharp increase in the fuel flow, and this might lead to a pressure drop or increase in the line going to furnace 1. If this preheating furnace is the only one connected to the main fuel line, or that you manage to keep the pressure variations under control, well, then there are no fuel pressure load disturbances, and then you can of course implement the simplest solution, and the simplest solution is a single loop control of the output temperature directly on the control valve. You only have one controller to tune. You do not need a sensor to measure the fuel flow, right? And you do not need to implement this interlock management, right? So the solution is a lot simpler. But if there is once in a while a load disturbance, then you'll react much more slowly. Let us summarize things. The main control objective was to maintain the product temperature at the output of the preheating furnace at a given set point, and therefore we had chosen this PV. We had identified two candidate MVs, but if there are load disturbances, pressure load disturbances, and the fuel flow measurement is available, then you can implement a cascade, and this cascade control will reject pressure disturbances, pressure load disturbances. Note that you can reject those disturbances without a sensor because they are indirectly captured using the fuel flow measurement, right? We had seen that there are other disturbances acting on the output. If they are measured, they can be rejected, but you'll need to implement a feed forward. So those two candidates that are used for feed forward, if measured, are the product flow at the input, right, and the product input temperature Ti. Here we will use an energy balance to compute the feed forward fuel flow, so we will be able to calculate the fuel flow that is necessary in order to make sure that the flow of product at an input temperature Ti is heated to an output temperature To, right? And here we use an energy balance, but in some cases it could be, for instance, a mass balance. Each time that you see an operator take a calculator to kind of compute what input value, what manipulated value it would use, there is a big possibility that what he's doing is either a mass balance or an energy balance. So have a look at what he's doing and use the ID for feed forward. So let us have a look at this energy balance feed forward. What we'll do is equate the required heat flow. This is the energy that you need to warm up the flow of product from its input temperature to its output temperature, and the output temperature will be, in this case, the set point temperature, and we'll equate it to the delivered heat flow. This is the heat that corresponds to a certain fuel flow. Of course, what we'll do is neglect all the losses in the preheating furnace. The required heat flow is expressed in joules per second, and it is given by this formula, and it's kind of intuitive. It is of course logical that this required heat flow is proportional to the product flow in cubic meter per second. It is also logical that it is proportional to the temperature difference between the output and the input, between the temperature set point and the input temperature, and it is of course also proportional to the specific heat of the product, the amount of joules that you have to use to warm up 1 kilo of the product by 1 Kelvin, right? And to make sure that everything is working, you have to multiply by the product density. If you multiply all these units, you will end up with something in joules per second. The delivered heat flow is also expressed in joules per second, and again it's kind of obvious that it is, well, proportional to the fuel flow and proportional to the fuel heating value. And to make sure that everything is correct with respect to the units, you have to multiply by the fuel density, and you can check that using this formula over here. You'll have something in joules per second that will correspond to the delivered heat flow. Well, if we neglect the heat losses in the preheating furnace, we can equate the required energy and the delivered energy, and this is the equation that you obtain. Okay, so we are interested in the fuel flow, so we can isolate the fuel flow, and this is what you obtain. And what we'll do over here is that we'll say that this is the parameter K, and this results in a feed-forward law that in theory is capable of steering the output temperature to its set point. So we'll use this feed-forward law and we'll replace this one by the output temperature set point, right? Of course, in practice, K is not known exactly, and there might actually, as we've seen before, be fluctuations of the heating value and the specific heat of the product, right? Also, these quantities over here, so the product flow and the input temperature, come from a measurement, so they are not known exactly as well. Of course, you have to take the losses into account, and of course there are also dynamic effects, small dynamic effects that have to be taken into account. So you'll have to combine this feed-forward law with feedback. We'll see later on in the course that you always have to combine feed-forward with feedback. Here you can see that the feed-forward gives a multiplicative effect for the product flow and an additive or subtractive effect for the input temperature. So in summary, we had been controlling the output temperature, right? And we were doing this using a cascaded solution to be able to reject pressure, fuel, load disturbances, right? And we had come to the conclusion that we can also reject other disturbances here at the output of the process if they are measured, and you can do this using feed-forward. We have just looked at the energy balance based feed-forward, and this is how it looks like, right? And this is indeed implementing the feed-forward that we have considered previously. So here you have the fuel flow coming from the feed-forward, right? And it is K times, well, the measured product flow times the temperature set point, so that this is what we desire here at the output, minus the input temperature. And it's kind of a very intuitive feed-forward. As you can see, if the temperature here at the input is what you desired, well, you do not need any fuel flow, and well, the larger the discrepancy between the input temperature and the output temperature, the more fuel flow you require, right? And this fuel flow is of course proportional to the product flow. The feed-forward is never exact, so here what we'll do is use the controller to compensate for the fact that this computation is not exact. So what will come out of the controller is the fuel flow and we'll denote it as fuel flow coming from the feedback. Now the controller will be correcting the feed forward action, and this sum is the fuel flow, and we'll set it as a set point for our, well, slave fuel flow controller. This is the control structure that we have arrived at, but in the form of function blocks, right? As you can see here, you can recognize the cascaded solution. Here, the primary or master temperature controller that sets here the fuel flow. Okay, the fuel flow here is a correction on what is obtained using the feed forward, right? And the sum of the fuel flow correction plus what is obtained using the feed forward is sent to the slave or secondary controller that actually controls the fuel flow by controlling the opening of the fuel flow control valve. The feed forward, right, is acting using the input temperature and the product flow, right? The output temperature set point is sent to the feed forward and to the master PID controller. The type of control scheme that you see over here is the type of control scheme that you might find, for instance, in a PNID. It is not really the way things are implemented in reality. This type of control scheme is produced to explain how the control scheme is working, right? In reality, this MV, that is the sum of this MV coming from the feedback and this MV that is coming from the feed forward, has to be limited, right? There is an MV min. In this case, it would be, let's say, 0 liters per minute, of course. And there is also an MV max, right? For instance, it could be, I don't know, 10,000 liter per minute. This sum, what is coming from the feedback and what is coming from the feed forward, needs to be limited. Since this adding over here is done after the PID controller, it is difficult or impossible to do this kind of limitation, right? So this is why this is not really implemented this way. So what we'll do is erase things over here and have a look at how it is really implemented, right? So what is done is that the output of the feed forward goes to some input of the PID controller that is often called MV feed forward. We'll discuss this later in the course. And this adding, right, this plus, is done inside the controller, right? And what is produced at the output MV is what is coming from the feedback and what is coming from the feed forward, but everything is done in such a way that you can implement the limitations on MV min and MV max. And this limitation is done in such a way that there cannot be any integrator wind up.